Applications of differentiation. Maximum and minimum problems. Differential calculus is ideally suited to maximising and minimising real-life quantities. To do so, however, we first have to build a mathematical model of the problem. This usually involves introducing variables, letters, to represent measurements and formulating expressions for the quantities to be maximised or minimised. Because these questions can vary so much, it is important to take a structured approach. This allows us to break a large, difficult problem into a number of shorter, more manageable steps. So, to tackle a max-min modelling question. Step 1. Identify the variables and constants to be used in the question, very often with the aid of a diagram. The variables may be identified for us in the question, or we may have to introduce our own. Read the question and identify the quantity that is to be a max or min, greatest, least, most, largest, etc. Give this quantity an obvious name, for example, V for volume, A for area, etc., and write this quantity in terms of one or more of the variables. So this is important. Write this quantity in terms of one or more of the variables. If the quantity to be a max or min is expressed in terms of one variable, then go to step 4. So then go straight down to step 4. On the other hand, if it is expressed in terms of two or more variables, then we need to go to step 3. Okay, so step 3. Read the question again and find the constant expression linking the variables. Use this expression to write one variable in terms of the other, and then write the quantity to be a max or min in terms of one variable. We must not get to step 4 until we have the quantity to be a max or a min in terms of one variable. So for two or more variables, we use step 3. So if the quantity to be max or min is expressed in terms of one variable, we go straight to step 4. Otherwise, we use step 3 to get our quantity to be max or min expressed in terms of one variable. So if it's already in terms of one variable, we go straight to step 4. And if it's not in terms of one variable, we use step 3 to make it in terms of one variable. So step 4, differentiate the quantity to be a max or min with respect to the one remaining variable and put the derivative equal to 0. Then solve this equation. If there is only one solution, then it must be of the required type. However, if there is more than one solution, then we will need to check each using the first derivative test or the second derivative test to identify the one we require. Sometimes there will be more than one solution, but by considering those which make sense or are physically possible, we may be able to identify the required solution without testing. Step 5. Read the question yet again to make sure that all the requirements have been found. For example, if in step 4 we have found r, a radius, and we are asked to find a volume, then the value of r must be used to find the corresponding volume. So very important to go back at the end and read the question again. The area of a rectangle is 12 meters squared. Find the dimensions of the rectangle if the perimeter is to be a minimum. So as soon as we hear maximum or minimum, we want to think differentiate. So step 1, identify the variables and constants to be used in the question, very often with the aid of a diagram. The variables may be identified for us in the question, or we may have to introduce our own. So we're going to draw out the diagram of a rectangle, and we will have to introduce our own variables, so we can let the width be x and the length be y. Read the question and identify the quantity that is to be a max or min, so greatest, least, most, largest, etc. Give this quantity an obvious name, for example V for volume, A for area. So perimeter is what needs to be minimized. So our dimensions are going to be x meters and y meters for a rectangle, the perimeter P to be a minimum, and now we have to write this quantity, so we have to write the P, the perimeter, in terms of one or more of the variables. So our variables are x and y, so we have to write P in terms of x and y. So the perimeter is equal to the length plus the other length plus the width plus the other width. So since the lengths are going to be the same, it's going to be P equals 2x, and the widths are going to be the same, so it's going to be plus 2y. So here we have an equation or a formula for the perimeter of this rectangle. So P equals 2x plus 2y. Notice that we have two variables, x and y. So therefore we have to use step 3. Step 3. Read the question again and find the constant expression linking the variables. So reading the question again, the area of the rectangle is 12 meters squared, so this is going to link the variables. We use this expression to write one variable in terms of the other. So we know from the question, given in the question, the area equals 12. So the area is going to be the length times the width, so x times y equals 12. And we want to write one variable in terms of the other. So we can say y equals 12 over x. So y is now written in terms of x. We could have obviously done it the other way around, x equals 12 over y. So we have wrote one variable in terms of the other, and then we write the quantity to be a max or min in terms of one variable. So our perimeter is equal to 2x plus 2y. So we're going to swap this y for 12 over x. So thus P equals 2x plus 2 times 12 over x. And that gives us 2x plus 24 over x, because 2 times 12 is 24. And 24 over x is the same thing as 24x to the power of minus 1. So the perimeter is 2x plus 24x to the power of minus 1. So now we have the perimeter in terms of one variable, which is what we want. So if the perimeter had already been written in terms of one variable, we would not have had to do step 3. We could have gone straight to step 4. So step 4, differentiate the quantity to be a max or min with respect to the one remaining variable, and put the derivative equal to 0, and then solve the equation. So we started with P equals 2x plus 2y. So we have a formula for the perimeter. We swapped the y for 12 over x because we let y equal 12 over x, and we got this from the area. And we multiplied out the brackets and simplified until we had 2x plus 24x to the power of minus 1. So this is our formula for the perimeter. So now we're going to differentiate this, which is P. So we're going to differentiate P in terms of x. So differentiating 2x, we get 2. Differentiating 24x to the power of minus 1, we get minus 24x to the power of minus 2, which gives us minus 24 over x squared. So now we're going to put dp dx equal to 0. So 2 minus 24 over x squared equals 0. So 2 equals 24 over x squared. So x squared equals 12. So x equals the square root of 12. And this is as minus root x is not possible, because we cannot have a negative length or a negative width. So we differentiated. We put the derivative equal to 0. and then we solved. Although there were technically two solutions, this was the only solution that made sense, so x is equal to root 12. Step 5. Read the question yet again to make sure all the requirements have been found. So the area of the rectangle is 12 meters squared. Find the dimensions of the rectangle if the perimeter is to be a minimum. So we got x equals root 12 meters. So y is going to be 12 divided by x, which is 12 divided by root 12, which is root 12 meters. So 12 meters, root 12 meters and root 12 meters are the required dimensions. So the width being root 12 meters and the length being root 12 meters. So here we have the same question again, just without all the steps written in to have it a little bit neater and easier to see what's going on. So just a reminder again. The area of the rectangle is 12 meters squared. Find the dimensions of the rectangle of the perimeter that is to be minimum. So we started with drawing out our little sketch, labelling the length and the width x and y. So we let the dimensions be x meters and y meters for the length and the width. And we let the perimeter P to be a minimum be P equals 2x plus 2y. And it was in terms of two variables, so what we had to do was use the information in the question to rewrite this in terms of one variable. So we were told in the question the area is 12 meters squared. So what was given was that the area is equal to 12. So the area is the length times the width, so x times y equals 12. So rewriting in terms of one of the variables, it didn't really matter if it was x or y. So we have y equals 12 over x. So then we take our perimeter and we swap the y for 12 over x. We multiply out the brackets and simplify. Then when we have our perimeter in terms of one variable, in this case x, we differentiate with respect to that variable. So we differentiate the perimeter with respect to x and we get this. We let it equal to 0, we let the derivative equal to 0 and we solve for x. And then using our x value, we found our y value. So we found our length and our width. There are some important points to remember. Many of the formulae for areas and volumes can be required in questions involving plane figures and solid objects. Most of these formulae are given in the formulae and tables. If in a max-min problem we are asked to derive an equation, it is almost certain that it will be required as we proceed with the question. If we are told that a certain quantity is constant or given, then we put it equal to c, a constant. We put it equal to some constant. For questions connected with the xy plane, if a point lies on a curve, we can use the fact that the coordinates of the point satisfy the equation of the curve. So here we have another example. A cylinder of radius r and height 2h is to be cut from a solid sphere of a radius a. So here we have our cylinder that has a height of 2h and a radius of r, and it's to be cut from a solid sphere that has a radius of a. The circumference of the top and the base of the cylinder lie on the sphere, as is shown opposite. So the circumference of the top and the base of the cylinder lie on the sphere, so it's touching the sphere. Question 1. If V is the volume of the cylinder, show that V is equal to pi times a squared h minus h cubed. So we're going to draw a vertical section of the sphere and the cylinder as shown opposite. So here we have a vertical section. So if you were to imagine if you were to get a chainsaw and slice right the way through our sphere and cut it into a hemisphere, this is what you would see on the inside. So our cylinder is now in the shape of a rectangle. Our sphere is obviously in the shape of a circle. And the A, which is the radius of the sphere, is now a hypotenuse of a right angled triangle. So let O be the centre of the sphere. So O is the very centre of the sphere. And O joins to P along A, the radius. And let P and Q be the points shown. So P joins to O, connecting together the radius, which is A, and it is the top right corner of the cylinder, or in this case it's a rectangle, and Q is the bottom right corner of the rectangle. Let S belong to PQ, such that OS is perpendicular to PQ. So we plot a point S so that OS is perpendicular to PQ. So now we have a right angle in our right angle triangle. Then, by geometry, PS equals H. So if from P to Q is 2H, then from P to S must be H. Because if this is a perpendicular, then this is the midpoint. So this is one of our circle theorems. So PQ is a chord of our circle, and the chord meets the center, or connects to the center, using a line that if it is perpendicular, if the two lines meeting are perpendicular, then this must be the midpoint of the chord. So if this is the midpoint of the chord, it's the midpoint of the line PQ, and if the length of the line PQ is 2H, then the length of PS must be just H, because half of 2H is H. So here's our right angle triangle. This is A, the hypotenuse, this is H, and this is R. So this is the radius of our cylinder. So if we look back here, this distance here is R, the radius of our cylinder. By Pythagoras' theorem, R squared plus H squared equals A squared. So A is the hypotenuse. So the square of the hypotenuse is equal to the sum of the square of the other two sides. So R squared equals A squared minus H squared. So we've just solved for R squared. So now that we have R squared, we can swap the R squared in the formula. So this is the formula for volume. So volume equals pi R squared H. So this is the formula for the volume of a cylinder. So we can swap that R squared for A squared minus H squared, since we have solved for R squared. And then multiplying out, we get the volume equals pi times A squared H minus H cubed, which is what we were asked to show. So the volume of the cylinder is V equals pi times A squared H minus H cubed. Part 2. Find, in terms of A, the dimensions of the cylinder of maximum volume that can be cut from the sphere. So when we hear maximum or minimum, we think differentiate. So in part 1, we were told that V, the volume, equals pi times A squared H minus H cubed. Now we differentiate V with respect to the one remaining variable H. So dV dH is equal to pi times A squared minus 3H squared. So we just cancel out the H, so we're left with A squared. And for minus H cubed, we bring the 3 down in front and reduce the power by 1. So we get minus 3H squared. Now we put dV dH equal to 0, so we put the derivative equal to 0. So we have pi times A squared minus 3H squared equals 0. And then we solve for H. So we can cross off the pi, because technically if we want to get it over to the other side, we'd be dividing both sides by pi, and 0 divided by pi is just 0. So we have A squared minus 3H squared equals 0. So solving for H squared, getting the H squared on its own, we would first of all bring the A squared over the equal sign. It would become minus A squared. And then we would divide by the minus 3. And we would end up with H squared equals A squared over 3, because a minus divided by minus is a plus. And then bringing the squared over the equal sign, the square root of A squared is A, and the square root of 3 is root 3. So solving for H, we get H equals A over root 3. And since H is a height and must be positive, we cannot use the other possible value, which is minus A over root 3. So this is not possible because we can't have a negative height. So now we have H. H is equal to A over root 3. So this H here is equal to A over root 3. we now want to find r. So again, using Pythagoras' theorem, we know r squared is equal to a squared minus h squared. We're going to swap the h for a over root 3. So r squared is equal to a squared minus a squared over 3, which gives us 2a squared over 3. So then solving for r, so bringing the squared over the equal sign, we get root 2a over root 3. So r is equal to root 2a over root 3. So now we know what r is, the radius. So the dimensions of the cylinder of maximum volume are a radius of r equals root 2a over root 3 and a height of 2h, which equals 2a over root 3. So the cylinder has a radius of root 2a over root 3 and a height of 2 times h, and since h was a over root 3, 2 times that is 2a over root 3. So this is the height now of our cylinder. Part 3. Find in terms of A the volume of this cylinder. So the maximum volume of the cylinder is, so our formula is V equals pi times a squared h minus h cubed. We got that from part 1. And we know that the h is a over root 3. We got that from part 2. So swapping each of those h's for a over root 3, we get the volume equals pi times a squared times a over root 3 minus a over root 3 cubed, which is pi times a cubed over root 3 minus a cubed over 3 root 3, which is pi times 3a cubed over 3 root 3 minus 3a cubed over 3 root 3. So this is our common denominator. And root 3 divides into 3 root 3 and leaves us with 3, so that's where the 3 comes from. And 3 root 3 divides into root 3 once, so we're just left with a cubed on the top. And then subtracting and multiplying in the pi, we get the volume equal to 2 pi a cubed all over 3 root 3. You should note the following about example 2. As there was only one physical possible value for h, for which dv dh is equal to 0, we are allowed to assume that this gave a max. If required, we could have verified this as follows. d squared v over dh squared equals minus 6 pi h, which is negative when h is equal to a over root 3. Point 2. The range of possible values of h was h greater or equal to 0, less than or equal to a. There is a theorem in maths which says that if a function is differentiable on a closed interval, such as v equals pi times a squared h minus h cubed, is on the interval 0, a, then its absolute maximum and its absolute minimum must occur either at a turning point or at an end point of the interval. At h equals 0 and at h equals a, v is equal to 0, the volume is equal to 0. Thus, the minimum possible value of v is 0. Pxy is a point on the curve y equals x minus 2 squared in the domain x values between 2 and 8. So here we have the point xy. And here we have the curve y equals x minus 2 squared. And the domain goes from 2 to 8. Q is the point 8, 0. And R is on the x-axis. So R is on the x-axis such that PR is perpendicular to RQ. So PR is perpendicular to RQ. What value of x maximizes the area of the triangle PQR? So let A be the area of the triangle PQR. So PQR, this triangle here, that is right angled because it's perpendicular. And we know that the area of a triangle is area equals a half times base times height. So the area is a half times RQ times PR. So the base is RQ and the height is PR. So or Q is 8 minus x, as or is equal to the point x comma 0. So this point here is x comma 0, so it lies on the x-axis. So or Q must be 8 units minus x units, which will leave us with the in-between. So that's why or Q is 8 minus x. And then P or is y, because this is y on the y-axis, and this is the point y. So if this is the point xy, this must be x on the x-axis, and this must be y on the y-axis. So we can swap the y for x minus 2 squared, as p is on the curve y equals x minus 2 squared. So we can swap that y for x minus 2 squared, because that's what the curve is equal to. So we have area equals a half times 8 minus x times x minus 2 squared. So we want to differentiate this, so we're going to use the product rule. So we're going to take the half, which is the constant outside, and then we're going to differentiate what's on the inside. So this is the u, and this is the v. So we write down the u, and then we differentiate v with respect to x. So differentiating x minus 2 squared, we use the chain rule, so we have 2 times x minus 2 to the power 1, which is 2 times x minus 2. Then we have our plus, we write down the v, which is x minus 2 squared, and then we multiply that by du dx. So the derivative of minus x is minus 1. Next we multiply out the brackets, and we simplify, and we get down to dA dx equals a half times minus 3x squared plus 24x minus 36. So we were asked what value of x maximizes the area of the triangle PQR. So when we hear maximize, we think derivative, so we differentiated. And now we put the derivative equal to 0. So we let this equal to 0. We divide both sides by a half to get rid of that half. And then we change the signs, so we end up with positive x squared minus 24x, positive 36. We divide across by 3, getting x squared minus 8x plus 12. We factorize, getting x minus 2 times x minus 6. And we solve, getting x equals 2 and x equals 6. As we were told in the question that x is between 2 and 8, x equals 6 is the only physical possible solution. Thus, x equals 6 gives a max value for a. So in part 1, we worked out that a, the area of this right angle triangle, is equal to a half times 8 minus x times x minus 2 squared. So now we're going to swap each of those x's for 6. So we have area equals a half times 8 minus x times x minus 2 squared. So swapping each of those x's for 6, because x equals 6 will give us a max value for a. We have the maximum value to be a half times 8 minus 6 times 6 minus 2 squared, which gives us 16. So the maximum value for a is 16. So the maximum area of the triangle PQR is 16. For questions involving business and economics, we should note the following basic ideas. So these will need to be learnt off. So revenue equals quantity sold, so the amount sold, multiplied by the price per unit. And profit equals revenue minus cost. A company sells Q items at a unit cost of P euro. The number of items that can be sold is linked to the unit cost price by the equation P equals 16 minus 3Q. The total cost in euro C of Q of producing these Q items is given by C of Q equals a third Q cubed minus 4Q squared plus 8Q plus 3. Part 1. Find the expression for the profit function P of Q. So first of all, we must get an expression for the revenue. So let the revenue be R of Q, and we know revenue is equal to quantity sold multiplied by price per unit. So R of Q is equal to P, which is the price per unit, multiplied by Q, which is the quantity sold. So R of Q is equal to 16 minus 3Q times Q. So P is equal to 16 minus 3Q, and Q is just Q. So multiplying, we get R of Q equals 16Q minus 3Q squared. Then profit equals revenue minus cost. The revenue is R of Q, and the cost is C of Q. So R of Q is equal to 16Q minus 3Q squared, so we got that from here. And C of Q is equal to a third Q cubed minus 4Q squared plus 8Q plus 3, which is from the question. So simplifying, we get P of Q equals minus a third Q cubed plus Q squared plus 8Q minus 3. Part 2. Calculate how many units Q that must be produced to maximize the profit. So, to maximize, we differentiate, we equal to 0, and we solve. So P of Q equals minus a third Q cubed plus a Q squared plus 8Q minus 3. We got this from part 1. Thus, dP dQ, so the derivative of P with respect to Q, so basically just differentiate this, is minus Q squared plus 2Q plus 8. So we let the derivative equal to 0, that's step 2 of our maximizing steps. So we have minus Q squared plus 2Q plus 8 equals 0. We change the signs, we factorize to get Q minus 4 times Q plus 2, and then we solve to get Q equals 4 and Q equals minus 2. As Q is greater or equal to 0, Q equals 4 will maximize the profit. Part 3. What is the maximum profit? So we know that P of Q is equal to minus a third Q cubed plus Q squared plus 8Q minus 3. We got that from part 1. So the maximum profit is going to be P of 4, which is equal to minus a third times 4 cubed plus 4 squared plus 8 times 4 minus 3, which is equal to 71 over 3, which is 23.67 euro to 2 decimal places. So Q equal to 4 will maximize the profit. So Q equal to 4 will maximize the profit. So we got Q equals 4 in part 2.